Okay, hello and welcome back. In this video, we're covering section 5.1 called Basic Rules of Exponents. So in this section and the following two sections, we're going to be looking at working with exponents both on numbers and on variables, and there's a handful of rules that come along with that. And it's super important to get comfortable with these, and it will make solving more complicated problems a lot easier if we can navigate around how different exponents will affect the elements of that problem. So let's start out with just evaluating some exponential expressions. So some expressions involving exponents. So they give this definition in the textbook for an exponential expression being something in the form of a to the power of n. So the power is that little number that is above the letter. You can read that as the exponent. And we can expand it out. If it's a to the power of n, that means it's a times itself n times. And it'll make a bit more sense when we see some specific examples. But we call this letter a the base, and n is the exponent. So let's apply this to some specific examples. So this first one is 2 to the fourth power. So the 2 we would call the base, and the 4 is the exponent. So what this means is 2 times itself 4 times, or we can expand this out as 2 times 2 times 2 times 2, which should give you 16. 2 times 2 is 4, so we have 2 of those. We can view this, we had to do this by hand, we can view this as 4 times 4. So overall, we'll get positive 16 as our result. In part B, B and C are interesting because they look similar, but we'll get different results. In part B, we have in parentheses negative 2 to the fourth power. So this time the base is negative 2. It includes the negative. We'll see that won't be the case for part C. And we still have 4 as our exponent. So this means the base times itself 4 times. So negative 2 times negative 2 times negative 2 times negative 2. So will the result be positive or negative? We still have 4 2's multiplied, so we'll get a 16. But the question is, will it be positive 16 or negative 16? Well, negative 2 times negative 2, negative times a negative gives you a positive. So positive 4, negative 2 times negative 2 here again gives us a positive 4. So we do end up with positive 4 times positive 4, which will give us our positive 16. And this will be true anytime we're raising some negative to an even power. It's going to end up canceling all of the negatives. So let's look at part C. C is just negative 2 to the fourth power. So they don't include the negative in parentheses like in part B. So in this case, our base would just be positive 2. And the negative is out there in the front. So this would be negative and then your 2 times 2 times 2 times 2. So we'll get the 16, but then the negative will apply to the 16. So this result would be negative 16. So you just have to be careful. The use of parentheses is pretty critical, and then especially if you're typing this into a calculator, and you can try this out. If you just type negative, like part C, oops, if we just type negative 2, like the negative button, and then 2 to the fourth power, you'll get negative 16 because it's going to evaluate it as we did here. Whereas if your base is -2. If you're trying to raise the whole quantity -2 to the fourth power, you'd want to use parentheses in your calculator as well, like how it's shown here. That will give you the correct positive outcome. So our second section is on what's called the product rule for exponents. This is when we multiply two things that have exponents together. And they give us this rule here. If a is any real number, then let m and n be positive integers, then we get this property, and I'll write it out here. So some number to some power times that same number to some other power, and they do have to be the same, these two bases. If the bases are the same and we have two different exponents and things are multiplied, this combines together into that same base with the sum of the two exponents. So how does this work? Let's say if we had, and let's just keep the a's, like a cubed times a to the second power. Well, a cubed, that's like a times itself 3 times. And then this is multiplied by a squared, so a, 2 a's basically. So we have 3 here and 2 here. So altogether, there should be 5 total a's. So this can be written as a to the 5th power. Oops. So we can just add the exponents together. So let's do a couple examples. So for a, we have 2 squared times 2 to the 4th power. Yeah, that's like 2 2's multiplied by 4 2's, so there should be 6 total. 2 to the 6th power, which if we evaluate that, we should get 64. Part B, this will work with variables too. We have x to the 9th power times x to the 6th power. So 9 x's multiplied by 6 x's, this is x to the 9 plus 6 power, or x to the 15th power. Part C, we have 5 times c cubed times 7 times c to the 9th. So now we have some numbers involved in front of our c variable. Well, we can rearrange this. We can make this 5 times 7 times c cubed times c to the 9th. Multiplication has this property where we can just rearrange the components of the multiplication. So that means this can be written as 5 times 7 times c to the 12th power. We can add those exponents together. And then 5 times 7 is 35. So 35c to the 12th power. So if we have some sort of mixture like this, we can end up just multiplying these coefficients, the 5 and the 7, and then add the exponents together. Part D has multiple terms, but the same rule will apply. So we have negative k to the 8th power times negative k times negative k to the 11th power. And there's no exponent here, but we can say this is technically to the first power. That will help in adding things up. So our base is negative k, so that would stay the same. And then we would add the exponents. So 8 plus 1 plus 11. Looks like that would add up to 20. So negative k to the 20th power. So if we have a multiplication where the base is the same, like we saw with each of these, and the exponents are different, then the result is that same base with the sum of the exponents. We can also raise a power to another power. So that's what they're calling the power rule here. This is the power rule for exponents. So what they're saying is if you have some base to some power m raised to another power n, this results in the multiplication of these two powers, m times n. So let's think of an example. Let's say we have a squared raised to the third power. That means we have three a squareds. So this could even be expanded out to a squared times a squared times a squared, because we're multiplying it by itself 3 times. And then we could apply that previous rule where we sum the results together, sum the exponents together. This would be a to the 6th power, which you get by multiplying the 3 times 2. We have 3 copies of these 2 copies of a. So copies of copies, if you see it that way. So let's practice using this property. So if we have something like 3 to the 8th power raised to the power of 4, this will evaluate as 3 to the power of 8 times 4, because we have 4 copies of the 8 copies of 3. So 8 times 4 is 32. And this just wants us to simplify, so we could further evaluate this. This would actually be a pretty big number, 3 to the 32nd power. Part B has us do this just with the general variable. So n cubed to the 7th power. This will simplify to n to the power of 3 times 7. So n to the 21st power. Part C. This looks a little bit more complicated, but same idea. We have, in parentheses, negative f raised to the 4th power, and then this is raised to the 3rd power. So our base is the negative f. That will stay the same. And then this will be now to the 4 times 3 power. So negative f to the 12th power. So if you have a power raised to a power, the powers will multiply. Whereas if we had a multiplication of 2 powers, the powers added together. We have another version or another extension of this rule. They're calling it the power rule for a product. So this is saying if you have two things multiplied inside parentheses, a times b raised to some power, you can essentially distribute the power to both terms. And this, I just want to note that this only works if things are being multiplied inside. This can become a to the power n times b to the power n. So let's just see an example. If we had, like, let's keep the a times b. Let's say this is to the 3rd power. Well, we would have 3 copies of a times b. So a times b times a times b times a times b times a times b. And we said earlier we can rearrange multiplication. Let's put all the a's together. A times a times a, and then all the b's together. Oh, I did one too many. It should only be 3 times. A times b times a times b times a times b. Yeah. So a times a times a times b times b times b. And then here we have 3 a's and 3 b's. So it can be written as a to the third power times b to the third power. So we can effectively distribute the exponent in there. But again, this only works if things are multiplied inside. We could not say if this was a plus b to the nth power, that this is a to the nth power plus b to the nth power. This is not true, but it's a really easy mistake to make. If we have something like this, we'd have to FOIL things out. And we'll see more of that at a later time. So let's practice using this one. Part A, we have in parentheses 9 times y squared. So this should be 9 squared times y squared, or 81 y squared. Part B, we have a fraction here, but the same rules will apply. We have 1/4 times t to the third power. So things are multiplied in the parentheses, so this can be written as 1/4 cubed times t cubed. So that means this is 1/4 times 1/4 times 1/4 times t cubed. So all those 4's will multiply. We haven't seen the rule yet, but this is like 1 cubed over 4 cubed. So 1 over 64 t cubed. In part C, we have 5 times c squared, all of this cubed. So we're going to start combining some of these rules together. Let's first distribute that power. This will be 5 cubed times c squared cubed. So here we have a power raised to another power. So those will multiply. This will be 5 cubed times c to the 2 times 3 power. So 5 cubed is 125. And then we'll have c to the 6th power. So 125 c to the 6th. And then part D, we have 3 times 6 times a times b squared. So the square, the second power, is only applying to what's inside the parentheses. This 3 is just kind of coming along for the ride. It'll be multiplied on the outside. So this would be written as, you can expand it out as 3 will stay the same, times 6 squared times a squared times b squared. 6 squared is 36, so 3 times 36 a squared b squared. And 3 times 36 should give you 108. Then we have our a squared and our b squared. All right, the last rule from this section kind of hinted at it earlier. This is if we have a division inside of parentheses raised to some power. It's kind of similar to our last rule. So this is saying if we have a over b, so some fraction raised to some power, this distributes to the numerator and the denominator. We can write it in this way. And vice versa, we can go both directions here. So if the powers are the same, we can bring it out uh, like this, inside where we have the rest inside parentheses, or we can go the other way. And this is a similar argument to the last one. Let's say we have a over b cubed. That's like a over b times a over b times a over b. When you multiply two fractions, just multiply the numerators and the denominators. So we have 3 a's on top and 3 b's on bottom. So the power just separately applies to the numerator and the denominator. So part A, we have 3 over 8 squared. So we can write this as 3 squared over 8 squared, or 9 over 64. Part B, 5 over x cubed. So same rules apply if we have variables. This will be 5 cubed over x cubed. 5 cubed is 125. So 125 over x cubed. And then part C, we have t over u to the 9th power. Well, that'll just be written as t to the 9th over u to the 9th. Not too bad. So the text gives a nice summary table for these rules that we've seen. So we have what they're calling the product rule. If you have a multiplication where the bases are the same and you have two different exponents, you end up adding the exponents together. And they give a nice example. P to the 4th times P to the 11th is P to the 15th. Then we have what they call the basic power rule. That's an exponent raised to another exponent. You end up multiplying the exponents together. So if we have like a multiplication, it turns the exponents into an addition. And then if we have an exponent raised to another power, it turns it into a multiplication. So it's always kind of like, in my mind, I see it as like one sort of operation step below what's happening. This multiplication becomes an addition. This raising of a power becomes multiplication. Just little tricks to try to remember. And then we saw if we have two things multiplied, so that's what they're calling a product. If a product is raised to a power, the power distributes to both terms. And same for a quotient. If we have some fraction raised to a power, it distributes to the numerator and denominator. All right, that's it for this section. So we evaluated some exponents, used the product rule, used the power rule for a product, and then the power rule for a quotient. So we'll continue with some special cases in our next video, but continuing the theme of working with exponents. Okay, that's it for this one. I'll see you next time.